Hi, we are Raphaela.
And Marcus from Climate Change AI.
Climate Change AI is an initiative that fosters impactful work at the intersection of climate change and machine learning by providing education and infrastructure, community building, and advancing discourse in this area. We are volunteers from academia and industry who believe that tackling climate change requires concerted societal action in which machine learning can play an impactful role. Climate change is one, maybe even the greatest problem of our times. Today, we will explore the myth that AI alone will magically save us from climate change.
Before we talk about AI and if it can save us from climate change, let's talk about climate change first. The human influence on the climate system is clear and growing. Scientists have a high confidence that global temperatures will continue to rise for many decades to come, largely due to the greenhouse gas emissions produced by human activities. Even though climate is defined by the trend of the meteorological variables over many decades, the consequences of a changing climate can be seen and felt. In fact, if you look at the period from 1880 to 2019, the warmest years have happened in the last 5 years. We can see the consequences almost yearly. New record-breaking droughts, floods, heat waves, and other extreme weather events occur. Already today, 11% of the world's population are vulnerable to such severe climate change impacts. And it's not distributed fairly, so it's often the regions on Earth that are affected the hardest, which contributed least to the changing climate. And this is not new. We have known about the climate impact of CO2, methane, and other greenhouse gas emissions for many decades now. However, emissions are still increasing each year worldwide. More CO2 has been emitted in my lifetime of a little over 30 years than in the 250 years before that. That is even though the IPCC, that is the Intergovernmental Panel on Climate Change, a body of the United Nations consisting of leading scientists and experts in climate change, has published their first report over 30 years ago in 1990. Additionally to the human activities, there are also other feedback loops that are natural that further increase the effects, like the albedo of Earth that is increased by the melting ice, or additional greenhouse gas emissions from the melting permafrost that strengthen the warming trend even more. And several of these processes can be seen as irreversible within, let's say, human timescales. And they are therefore considered important tipping points that should be avoided as much as possible. And the problem is, even if we stopped all additional emissions right now, this would not be enough, because CO2 and the other greenhouse gas emissions remain in the atmosphere for many years, sometimes even decades and several hundreds of years. And so all the current CO2 emissions are cumulative of all the human activities that happened over the last 100 years or so. Therefore, when talking about actions against climate change, we cannot talk anymore from stopping global warming. We can only say we are limiting or mitigating climate change. So climate change mitigation is one important pillar of the fight against climate change. And with greenhouse gases being the main source of the current climate change, the most important mitigation strategy is the reduction of greenhouse gas emissions. The IPCC set the goal of net zero greenhouse gas emissions until 2050 in order to keep global warming to 1.5 degrees above pre-industrial levels. Just as a comparison, we already reached 1 degree warming, so we only have half a degree left. But what does net zero mean? As we will see, many of our processes emit greenhouse gases. So avoiding 100% of emissions is very, very hard and very expensive and may even be infeasible. Therefore, the goal is to achieve a balance of the amount of greenhouse gases that are emitted by us humans to the amount that is removed from the atmosphere by sinks of carbon. Those sinks can, for instance, be achieved by afforestation or other negative emission technologies, some of those that may still have to be invented. As the potential for those is limited, the most important action is the reduction of greenhouse gases right now. Let's talk about the 1.5 degrees of the IPCC goal. While 1 or 2 degrees may not sound like much, this half-degree difference between an increase of 1.5 to 2 degrees on average means, for instance, a doubling of the loss of plant species, triple the loss of insect species, and 2.6 times the population of the world that is exposed to severe heat. What 3 or even more degrees of warming on average would look like is not yet well understood. However, it will render areas of Earth uninhabitable that are now home to hundreds of millions or even billions of people and lead to very high loss of plant and animal species and many more dire consequences. Therefore, as I said, the most important action right now is avoiding as much as possible additional greenhouse gas emissions. This slide shows where the greenhouse gas emissions are coming from and what gases they are. So the most important ones are CO2 and methane, as you can see here on the right. In 2016, 73% of greenhouse gases came from energy, as you can see here on the left. Energy is needed in different sectors, most notably the electric energy supply and heating, but also transportation and manufacturing. The remainder can be attributed to industrial processes like cement production and most notably agriculture, as well as land use and forestry. To achieve a reduction of greenhouse gas emissions, all of these different sources need to be addressed. So it's not enough to just focus on one or the biggest contributors. Often these are also coupled. So as you can see in the middle, with buildings using CO2 for both the construction, but also the heating and the electric energy supply. So to limit global warming and climate change, again, the most important action right now is the reduction of greenhouse gas emissions. However, as we have seen, it cannot be stopped. So we are in any case on a heating path and there's going to be warming. Therefore, other actions are needed and that help us to adapt to the negative impacts of climate change. These actions and solutions take many different forms and are very different across the world. They may include better forecasts of extreme weather events. They may include the development of drought-resistant crops or more generally actions supporting ecosystems. So in summary, there are a lot of things that need to be done. The main two strains of actions are mitigation of climate change and the adaptation to a warming climate. Most importantly, greenhouse gases must be reduced as fast as possible and as much as possible. For the remainder, we need negative emission strategies. The IPCC set the goal of net zero emissions in 2050. So if we want to have a good chance of limiting the warming to 1.5 degrees above pre-industrial averages. So where do artificial intelligence and machine learning fit into this picture? Members of Climate Change AI and leading researchers from the AI community have co-authored a paper called Tackling Climate Change with Machine Learning. It summarizes the possible ways that AI and machine learning can play a role. So as for the general ways to approach climate change, also AI can support the mitigation and the adaptation of climate change. So for both, it describes example applications from over 800 sources. The paper gives indications of the kind of impacts that various applications of machine learning may have, and identifies common themes across the areas to show the strengths and weaknesses of AI over other methods. This slide gives an overview over some of the different application areas from the paper, in that machine learning and artificial intelligence can help the climate change mitigation and adaptation. For instance, in the buildings and city sector, example applications where AI can help is the optimization and control of HVAC systems or the collection of data from remote sensing. That is when you use image recognition and satellite data to gather data about the cities and avoid installing unnecessary sensors. In industry, machine learning can, for example, help in the design of new materials. It can, for example, optimize supply chain and shipping routes. In the transportation sector, there are example applications like the research and development of new fuels. Machine learning can, for example, help in optimally charging electric vehicles, and it can help to avoid using cars unnecessarily in the first place by optimizing the multimodal routing, by optimizing the pooling of people and freights in vehicle. But now, let's have a closer look at the electricity systems, a field that I have researched in over the past years while conducting my PhD. As shown before, energy is the main source of greenhouse gas emissions. Still, 84% of the primary energy are coming from fossil fuels, with only 16% coming from low-carbon sources like hydro and other renewables like wind and solar, but also nuclear power. Energy is needed in different sectors. Electric energy to power your devices directly, heating, transportation, but also manufacturing. One of the most important actions is to find different ways to reduce the energy consumptions in all of those sectors as much as possible. Secondly, another action to achieve a reduction in CO2 is to electrify as many of those sectors as possible and then increase the share of renewables and other low carbon energy sources in the electric system. To achieve a sustainable electric energy supply, the power systems are changing fundamentally. One trend we see is that the energy systems are transitioning away from a centrally organized supply of predictable carbon-based energy sources. Another trend is the digitization of the energy industry. This is needed because up until now, the network operators basically just had to keep an eye on one figure, basically the network frequency, which served as a good quality indicator for the stable condition of the network. So depending where you are, this may be 50 or 60 hertz, and if there's a slight deviation, they would just reschedule their centrally organized power plants. But now in a sustainable electric energy supply, there's a steadily growing capacity of fluctuating power generation. And this must now be integrated at all levels of the grid. So you have these large offshore wind farms and you have smaller solar installation on single family homes. And all the availability depends heavily on the weather. So one of the application areas where machine learning has already matured quite a lot and has improved the situation quite a lot is the forecasts in the electricity system. So many different things need to be forecasted to efficiently run an electric power system with high shares of renewables. One needs hyper-local forecasts of the renewable projection, but also of the load. But it's not only when the energy is produced, but also where. So remote sensing approaches, that is machine learning used together with satellite data, can be used to identify solar generation assets and help to better understand the state of the system. Another quite matured area is predictive maintenance. System operators have to manage a variety of assets that are typically spread out in the country, like power lines, transformers, and other assets. Here, algorithms can detect if such assets are degrading too fast and try to predict failures from data. Or, for instance, drones can fly along lines to detect any damage in the transmission lines, or wind turbines, or solar panels and other assets. Another way the electric energy system is changing is that traditionally the energy supply followed the demand. But now also the demand may be considered flexible and can adapt to the changing renewable supply. For instance, by optimally charging electric vehicles or shifting the operation of heat pumps. This is called flexibility. In my own research, I have, for instance, been working on forecasting the demand side at the household level using machine learning to predict peaks or model the distribution of likely consumption pattern. And then this can be used to model the flexibility also. Here you see, for example, work we have applied machine learning to make use of the inherent thermal energy storage capacity of the building mass and use the building itself as flexibility, so that it is essentially a battery for the power system.
On the adaptation side, AI can help prepare for the unavoidable consequences of climate change. For example, machine learning can help us understand climate and extreme weather events and can support planning for resilience and disaster management. Thus, AI can help in climate science directly. Based on the laws of physics, climate models depict the major drivers of the climate system: the atmosphere, oceans, land surface, and ice. Here, machine learning can be used to generate data for climate models and improve climate simulations. For example, data on ice sheets and sea level rise can be generated from satellite imagery. Climate models are important tools for local and national governments to predict the impacts of climate change, such as extreme weather events. Accurate predictions of climate impacts are important to determine the appropriate adaptation measures. Further, climate models build the basis for integrated assessment models, which allow us to predict global warming projections and the associated costs and risk. Integrated assessment models provide a quantitative description of key processes in society, the Earth system, and their interaction. Much as with climate system models, machine learning can be applied in any of the various submodels that make up an integrated assessment model. One set of applications involves deriving results at the appropriate spatial resolution, since different components of an integrated assessment model operate at different scales. Integrated assessment models are used to explore the technological and economic feasibility of climate targets and play a central role in the special report on global warming of 1.5 degrees Celsius, published by the IPCC, the Intergovernmental Panel on Climate Change. Based on the results from climate and integrated assessment models, AI can be used to assess the impact of climate change, for example, on the financial system. Climate-induced extreme weather events, flooding, droughts, and sea level rise can lead to unplanned and abrupt disruptions of production processes and supply chains. For example, changes in precipitation patterns, as well as increasing frequency and intensity of droughts, may reduce water availability for cooling purposes to thermal and nuclear power plants. Physical assets can be damaged and insurance costs can rise. In consequence, the physical climate impacts can have negative implications on firm performance, employment, and eventually on the whole economy. In addition to this physical risk of climate change, the financial sector is exposed to transitional risk. Moving towards a net zero economy means a shift in technologies and asset values in most sectors. Policies currently in place are projected to reduce global warming only to 2.9 degrees above pre-industrial levels. And for additional pledges and targets under the Paris Agreement are not in line with the 1.5 or 2 degree target. And this uncertainty in domestic climate policy implementation and financing requirements exposes the financial system to the risk of delayed climate action and a disorderly transition to a net zero state. Taking into account network effects of financial dependencies, a study by Battiston and authors found that a large portion of EU investors' equity portfolios are exposed to climate policy relevant sectors. AI can help to provide information on how climate change translates into these risks. For example, machine learning algorithms can be used to predict the effects of climate change on sovereign credit rating, as you can see here on this map. Another application of machine learning and AI is the computation of the social cost of carbon. The social cost of carbon is used to estimate the monetary value of all damages that would result from emitting 1 additional ton of greenhouse gases into the atmosphere. Since lowering greenhouse gas emissions is expensive and requires shifting resources away from other societal goals, the social cost of carbon is a crucial number for climate policy making. Putting a price on carbon and computing the actual damage allows policymakers to determine whether the costs and benefits of a proposed policy to curb climate change are justified. To estimate the social cost of carbon, the climate impacts are assessed in individual sectors, such as electricity consumption, agriculture income, labor supply, and also mortality, and then are brought together. Tools from AI and machine learning are leveraged to make the estimates more accurate. For example, here you have 2 examples from 2 different studies where machine learning has been applied to make these estimates of social cost of carbon more accurate and improve the different submodels that make up these calculations. The actions required to address climate change, both in mitigation and adaptation, require strong political commitment and immediate action at the local, national, and international level. The introduction of measures is based on complex collective decision-making that involves many stakeholders with different interests and priorities. Here, artificial intelligence can help to inform and support effective and efficient policymaking. For example, machine learning can be used to collect missing information relevant to decision-making. For example, data from social media and corporate websites can be analyzed and classified to gather information about public opinion and corporate behavior in response to policies. Further, machine learning can help analyze previous policy actions automatically and at scale by improving computational text analysis. For example, social network analysis and natural language processing, also called NLP, such as topic modeling, are used to understand the ways different non-state actors and subnational governments are taking action and how they align with each other and national governments, which is critical given the need for coordinated actions to achieve ambitious climate goals. In my work, I use NLP techniques such as topic modeling to measure a country's position on the introduction of a new global carbon market and their support for sound regulation. Carbon markets are a key policy tool to enable effective and cost-efficient greenhouse gas emission reductions. It's been applied in many countries already. The idea is to enforce a carbon price that reflects the social cost of carbon by putting a cap on the total amount of emissions. And experience with the existing market-based mechanism and the evaluation of policy alternatives are really critical to the design and the implementation of new carbon markets and new climate policies in other jurisdictions. Machine learning offers many applications here, for example, predicting prices via supervised learning or identifying the main price drivers. My current work involves applying machine learning to detect, but also deal with and ultimately prevent fraud in carbon markets. Okay, so we showed you many ways in which machine learning can help curb climate change mitigation and adaptation. But will AI save us from climate change? In those places where AI can help, it's only one piece of the puzzle. For instance, AI can help us better manage a power grid with many variable renewables. But strong policy and investment actions will be needed in order to incentivize the installation of large shares of renewables in the first place. Ultimately, AI is not a replacement for concerted action across policy, the private sector, and civil society, though it can be used to help facilitate the resultant climate change strategies. In addition, it's worth noting that while AI can be used to help climate change, it is a tool, and like other tools, it can be used in ways that contribute to greenhouse gas emissions as well. Greenhouse gas emissions can be attributed to AI in two areas. One is first is the direct effect, so greenhouse gas emissions from the computational requirements of training, developing, and using AI. And this includes the energy required for computational power and the emissions associated with the manufacture and disposal of hardware. Recent studies, such as the study by Strube et al., point out that the carbon footprint caused by some of the largest machine learning models, such as those used in natural language processing, can be comparable to flights or the life cycle of a passenger car. And then secondly, we have the indirect effect. So greenhouse gas emissions created by the application of AI. And AI is also being applied in areas that have a negative impact on climate change mitigation, and in those where the consequences are still poorly understood. For instance, machine learning is applied in the oil and gas industry to optimize business processes or to find better locations for oil platforms. Thus, AI is used to facilitate the extraction and burning of fossil fuels and can also contribute to climate change. In general, it can be assumed that the indirect effects on emissions from AI applications could be significantly more substantial than the effects from computing. But exact figures on this are not available. Currently, there's only very little data available there are only few studies that have been conducted on the magnitude of various effects of AI on greenhouse gas emissions. Thus, whether AI is generally beneficial or detrimental to climate protection is not easy to answer. Effects need to be considered in their entirety, and actions really need to be taken, especially where AI is being increasingly used and its application may be able to significantly affect greenhouse gas emissions. Nevertheless, there are many areas where AI is already being used successfully to reduce greenhouse gas emissions and adapt to climate change. There are many opportunities for machine learning applications here that still need to be explored. What we can say is that AI provides a really powerful tool, or actually many powerful tools, but it's not a silver bullet. In any case, AI applications should be developed in collaboration and ongoing exchange with the communities that will use or are otherwise affected by the technology to avoid unforeseen impacts and drawbacks. CCAI provides many digital resources to catalyze impactful work at the intersection of climate change and AI. You can visit our website for more information on our activities and subscribe to our monthly newsletter to keep informed about upcoming events, calls for proposals, and jobs, for example. You can also check out our newly created wiki if you want to learn more about AI applications to tackle climate change, or find resources to get started working at the intersection of AI and climate change. Or you can also interact directly with us or like-minded people in the bi-weekly meetups or in our forum. You can find more information on this also on our website. Thank you so much.
Yes, and thank you also from me, and I hope you enjoyed our talk, and yeah, maybe we can see each other at one of our activities and discuss if or how machine learning can help the fight against climate change.